Good morning. Welcome to the CEWIT conference, and welcome to the Smart Infrastructure panel. My name is Rong Zhao. I'm the moderator for this panel. I'm also the program committee chair for this. Thank you so much for everyone joining us this morning. So we have a really distinguished panel today. So thank you so much for making time out of your very busy schedule. So we have both industry speakers and academic speakers. So we will, each speaker will introduce themselves and give a short presentation, and that will be followed by a roundtable discussion, and and we'll take questions from. So just what you see the three tabs: chat, participants, and Q&A. So if you could put your questions in the Q&A tab, that would be wonderful. But certainly we will monitor both the chat and the Q&A. All right. So again, thanks so much for joining us for this Smart Infrastructure panel. So on the high level, we know, smart infrastructure technologies can help us enhance the way how we work, we live, right, and also how we learn. So it makes a great impact to our lives, altogether. But I think what I'm hoping to learn from our panelists is the details, right? So how do we really, what are the enabling technologies, and what are the specific opportunities that we have, in the turning existing infrastructure into smarter infrastructure and build brand new ones, right? And also, the panelists will help us understand the work, the processes, and the components, right? So, on a very detailed level. So I'm very much looking forward to that. So without further ado, let's kick this conversation off. Let me introduce Dr. Jonathan Lenchner. John is a senior technical staff member and master inventor at IBM T.J. Watson Research Center. So he's got a very distinguished career, very diverse, right? Being a mathematician, but worked a lot on very practical applications as well, and I look forward to hearing about a lot of these projects. So previously, he was also the chief scientist of IBM Research Africa in the labs of in Kenya and South Africa. He has developed robots to help with data center energy efficiency and for greeting visitors at the IBM labs. He also contributed to the Watson, as everybody know, and he has also worked on highly instrumented smart spaces and smart conference rooms, and highly instrumented war room to help professional sports. So we'll hear about that. So please, John.
Okay, so thanks a lot, Ron. My pleasure to be here, well, virtually. I've actually been at Stony Brook quite a few times in person, first time virtually. So let me share my screen here, see if that's going to work. Okay. All right, I think this is it. No, that's not it. Here it is. Okay. Oops. Okay, so can everyone see my screen?
Yes.
Okay, great. All right, so again, my name is John Lenchner, and I work at the IBM T.J. Watson Research Center, and these slides are just to give you a bit more detail about my work. Ron sort of introduced it nicely at a high level. So I've been at IBM since 1997, so 24 years in total. I began working on supply chain problems and then on e-commerce. And I transferred to research 3 years later in 2000. I built the game strategy component of the famous Watson Jeopardy playing system. So the Jeopardy playing system is most well known for its question answering capability, but there also is a strategy component to the game of Jeopardy that entails what squares to pick, what to bet on daily doubles and in Final Jeopardy and so on. And that's the component that I did. Then I've also created these two robots that Rong referred to. And also I've done a variety of other smart infrastructure projects that I'll outline in the next few slides. And then I spent 3 years, somehow this jumps in front sometimes. Okay, sorry about this. Okay, and then I spent 3 years as chief scientist of the IBM research labs in Africa. We had 2 labs, one in Nairobi, Kenya, and one in Johannesburg, South Africa. And most recently, I've fallen back on my mathematical roots, and I've been studying problems in theoretical computer science, and in particular, working on the famous P versus NP problem. Before IBM, I worked as a consultant in the hydrogeological field, looking at risk assessment of groundwater cleanups for the company Nittany Geoscience, and I also worked in mathematical finance. And my education is completely in mathematics. So I've got a BS from Dartmouth College, or BA from Dartmouth College, the equivalent of an MS from Cambridge University, and a PhD from a school that's now part of NYU. Okay, so the first project I'd like to tell you about is, I'm going to focus exclusively here on smarter infrastructure projects because that's the nature of this panel. I built a robot for data centers to map out the layout of equipment and measure the temperature and humidity distribution within the data center to minimize the cost of cooling. Okay, so you can see the robot in the picture. Actually, it's equipped with an iRobot Create base, which is the same as the Roomba vacuum cleaning robot, but without the vacuum cleaning attachment and with certain programmatic capability. We added a low-powered netbook computer. I'm saying this was about 10 years ago, so probably we would nowadays add a phone to do this work, but in those days we used a low-powered netbook computer, and there was also a downward-pointing camera for navigation to see exactly what was in front of us. Then a temperature and humidity sensors at 1 foot increments along the vertical pole to measure the temperature and humidity distribution. Then an RFID reader for tracking equipment. So there were also RFID tags on all the equipment in the data center. And finally, upward pointing ultrasound sensors to detect overhead obstacles. Okay, and in its heyday, these robots there were about 50 of them deployed at locations in 4 different continents, both IBM data centers and some of our customers' data centers. Okay, the second project wanted to mention is this smart conference room, what we call the Cognitive Environments Lab. So it's an experiment in incorporating speech and pointing and high bandwidth I/O, so vast number of screens and high fidelity audio throughout the conference room. And instead of using a mouse, you actually use a pointing device to move content around within this room, from within a monitor or from monitor to monitor, and also use your voice, of course. And this system was built as a large-scale multi-agent system with a single orchestrating agent. So this project, unlike the robot project, never really got beyond the point of a demonstration, but it was a very interesting project, and there's quite a lot of literature about the work we did. Okay, then an offshoot of this work was a war room that I developed to help with the analysis of trades and draft picks for the Toronto Raptors, a professional basketball team. And we use similar technology to that which we developed in that Cognitive Environments Lab or CEL, but without the voice. So we found from the CEL experience that voice was not a reliable enough source of I/O, so we did not use voice here. But we did employ a lot of AI and to help identify draft prospects and candidate win-win trades. Okay, so a good trade is one that makes you happy, but also makes the team that you're trading with happy. So we want optimal sort of win-win strategy opportunities. Then we finished this work in the middle of the 2015-2016 NBA season, and it was showcased at the 2016 All-Star Game, which coincidentally was also hosted in Toronto. And there's a lot of great press about this. And the Raptors, it turned out, built a better built a better and better team over the ensuing years, culminating in their historic championship season of 2018-19. And here's just a few pictures of that war room. So basically, it's this two big surfaces that act like just like a cell phone. You can move content around, and they're on the table. You have different workstations for the different people in the Raptors front or back office, where they analyze different scenarios, and then they can move content up to the front screen for everyone to look at. Okay, then another project that I worked on was in Kenya, an exciting project, something called Kenya Rapid for Resilient Arid Lands Partnership for Integrated Development. And the project was to spur more effective use of water infrastructure in the poor arid lands of northern Kenya. So many people know about Nairobi, how it's a booming tech hub, but actually much of Kenya is very poor, especially the north. And you have these nomadic people, very sparsely populated, but they live on the razor's edge of existence. And in order to survive, they have to find water. And international aid organizations over the course of years to make sure that these people don't slip into the clutches of the terrorist strongholds in Somalia and elsewhere have provided water infrastructure. But the sad thing is that the money has often gone to the building of wells. These wells fail over the course of time. They're mechanical devices. And these nomadic people look at this infrastructure. It often advertises that it's a gift from the American people, usually from USAID, the U.S. Agency for International Development. But then when the infrastructure fails, they blame everything on us. So this project, instead of focusing on providing new wells all the time, which is extraordinarily expensive, we tried to outfit the water infrastructure with solar-powered sensors to detect when the wells were starting to fail. And then furthermore, we tried to make sure that they were equipped with the means to maintain and fix the failing equipment as it was failing. Okay, then a last project that was mentioned in the introduction, I built a greeter robot for the IBM Yorktown Think Lab. And you can see the robot in the picture. It's a little humanoid robot, and it interacts with users through a spoken user interface, answering common questions and engaging in simple conversation. And it's built on top of the Aldebaran, now humanoid robotic base platform, and incorporates IBM's voice technology. Okay, so that's it. Thank you very much.
This is really interesting and really fascinating to see the the broad spectrum of projects that you've been involved in, and certainly being an avid basketball fan, I certainly remember the championship games back in 2019, the Raptors, and also the before that series clinching shot by Kawhi Leonard. I don't know if you watched the corner off balance.
Oh yeah,
shot.
that's Philadelphia. Yeah.
Yeah. So it's totally hero ball for sure. Yeah. So I just have one quick question on so it's very interesting to see that some of these projects, quite a few of these, you're exploring the different interactivity with the system, right? So, very much human in the loop, and also not just visualizing the data, but also using like a spoken interface, right? The speech. So can you comment on that in terms of you mentioned that, some of the challenges for that war room, but, can you talk a little bit more about that? Because I'm just thinking, like, for someone, say, working in the field, whether it is, maintenance, staff at a utilities, or someone working in a automated, semi-automated factory floor, doing inspections and things like that. So, the interaction. So can you comment on that?
Sure. Yeah, I think that experimented a lot with voice. It works in some contexts, seems not to work in other contexts, and it's certainly the future in many respects. I think for one-on-one interaction, and where your expectation of what's possible is done well, made clear, it's fantastic. And for example, the Alexa, the Amazon Echo is a wonderful little device, but you don't have any expectation that the device is going to have a sustained conversation with you. I think often we go wrong by leading people to think that we can really have a sustained conversation through a voice interface, which is really beyond the state of the art. I mean, you have GPT-3, which is pseudo, conversational, but it really, there's not a use case that would benefit a human being. For GPT-3 is great for demonstrations and for various things, but I think we're not yet capable of having sustained conversation. I think the voice didn't work so well in our cognitive environments lab, in that highly instrumented conference room. It was interesting. We had quite a few beautiful demos, but I think the technology never got beyond the level of beautiful demos. On the other hand, the technology worked okay in the case of a greeter robot for one of our research showcase labs. There, people didn't have clear expectations of having a conversation, and the robot got away with being able to answer simple questions, which people often had as they got into the room, and they thought the robot was cute. And that was all we were trying to do, have to deliver a cute little experience. And one of the most popular things, it was good at telling some ridiculous jokes. And the people got a kick out of it, but they had no expectation of it having long discussions. And so you got to be careful, I think, when you work with voice at this stage in the development of voice technology. Just make the user or a set of users completely aware that the technology is not going to have a sustained conversation, and I think you're safe.
Great, that's great, and I don't know if any of the other panelists wanted to chime in here, and I do have a few other questions, but we'll save them for the later conversation, because I do want to have our other panelists to jump into that conversation. So thank you again, John. Let's next up we'll have Dr. Christopher Niezrecki. So Professor Niezrecki is chair of engineering at University of Massachusetts Lowell. He's a very distinguished researcher, and really tremendous career engineer as well. So he is currently the co-director of the structural dynamics and acoustic systems laboratory, and leads the Center for Wind Energy at UMass Lowell. Dr. Niezrecki is also the director of the NSF Industry University Cooperative, or IUCRC, for wind energy science, technology, and research, or the acronym is WindStar, as you can see from the slide here. So Chris has been directly involved in vibrations, acoustics, smart structures, controls, and over 30 years, with more than 100 publications. Areas of current research include renewable energy systems, wind turbine dynamics, monitoring and inspection, structural dynamic and acoustic systems, smart structures, signal processing, structural health monitoring, optical sensing, and smart materials. Please go ahead, Chris.
Ron, can you hear me okay?
Yes.
Perfect. So I'm going to tell you a little bit about the research that's going on in the WindStar Center that I direct. So just a little bit about the center itself. It's a collection of two universities, mine, which is UMass Lowell in Massachusetts, and then UT Dallas is our partner institution. In addition to that, we have a collection of companies that includes OEMs like GE, owner-operators like Leeward, Pattern, EDP, Shell, etc., and quite a few other companies that represent almost the entire supply chain of the wind industry. Some of the research that we work on has to do with composites, blades manufacturing, structural health monitoring and inspection, which is an area that I'm interested in, and measurement controls of wind turbines and also wind plants. We're involved in energy storage, grid integration, and also foundations and towers. So what I'm going to do is to talk a little bit about some of the work that's going on in smart infrastructure, specifically focusing on wind. And so GE has been a leader in this. They've been working on a digital twin for wind farms for quite some time now. They've got over 15,000 wind turbines that are in the operating in the world. And so the question is, how do you take the information? How do you take SCADA data and sensor information and try to do something useful with it? And I'm not going to focus on what GE is doing, but I'll focus on what's going on within the center itself. So the motivation behind this is if you can create a digital twin, then what you can do is to really have virtual thousands of sensors, and you can identify damage equivalent loads. You can use it for damage prognosis, identify remaining useful life, how much life is left in your blades or various components. You can use it for predicting life extension. So, for example, one of the things that goes on in wind farms is swapping out blades for larger diameters and to increase power. And if you do that, well, how does that affect the life of the turbine that that's already in place? And also you can use it for different scenarios, such as seeing how much power improvements you can have if you change technologies. So for example, vortex generators, if you put them on, how much of a power increase you can get. So that's some of the motivation. But the question is, you need accurate data in order to do this, and you need accurate subcomponent models. And right now, the value of it is not really clear. And so one of the projects that Todd Griffith is leading is working on using accurate, fast aeroceroelastic models, and which include the turbine aerodynamics, the structural models, but also the cost models, and to try to perform, make decisions about a wind farm for all the benefits that I mentioned previously, ultimately trying to reduce a levelized cost of energy. But one of the questions is for these digital twins is the model really trustworthy? And then, how does it, there's a cost associated with this. And so is that cost worth the investment? And so those are some of the kinds of questions that he's trying to address and to try to identify, can this be used to make decisions about a wind farm or a wind turbine? There's another, on the aerodynamic side of things, if you want to know what's happening in the turbine-turbine interaction on a wind farm, you need some pretty advanced models. And the challenge is that if you have low fidelity models like Jensen and Park, they're not exactly accurate. But if you have super high fidelity models, then they're computationally expensive. And so there's a trade-off between having too high and too low and getting the results that you need. And there's a balance between that and being computationally expensive. So one of the other researchers, Valerio Jungo, is working on a project in which he's basically taking SCADA data and Met Tower data and using a mid-level model for RANs. So with that, he's able to come up with a virtual on the incoming inflow data, and then use that to calculate what should the turbine wakes be, how much power production is generated. With that, with this model that he's created, you can identify which turbines are underperforming for a given, for a set of inflow conditions. What is the turbine actually performing, what it should be performing, and with that you can identify if there's some sort of damage in the turbine, is there something wrong with the generator or some other component. You can also use this for wind farm layout if you include topography and because the topography of the land affects the wind flow and the energy resource. And so you can use this for modeling as well to try to understand why a turbine is not performing the way it's supposed to be. and also use it to study wind turbine-turbine interaction. So speaking of turbine-turbine interaction, what ends up happening if you look at this is basically the incoming flow, and there's a shearing that takes place in the atmosphere. And so when you have a wind turbine, what it does is it extracts energy from that incoming flow. And so the downstream energy has been reduced. And so the question is if you have a front row of turbines like the ones shown here, they influence the power production of turbines behind. And so Stefano Leonardi from UT Dallas is working on, well, what if you take the incoming turbines and if you basically change their profile. So if you can steer the wake, and that's what's shown here, you have a front turbine, you can see that there's a shadowing effect. And if we look at this graph here, as it's flowing, what is as the turbine gets yawed just slightly, the wake gets shifted, and I'll play that again. The wake gets shifted so that the back turbine, turbine 2, is no longer receiving a wind flow that's what we call dirty. And so ultimately, the first turbine may have a slight power decrease, but then on a wind farm, overall, you'll get an overall power increase over the entire wind farm. And so that's one of the things that he's looking at. Murat Inapolat, he's working on a project that's looking at using acoustic sensors inside of the blades to monitor damage. And so the idea is if there is a leading edge or trailing edge split, or if there's some damage due to lightning, or if there's a disbond, that will reveal itself in the acoustic signature inside of the blades. And so here's an example of that, a test that we did at the Wind Technology Testing Center. We had some damage in this blade that's laying on the ground. And so you can see that the sound emitted from that, you can identify where the damage is coming from. And so we're solving the inverse problem. So there's a damage or something like that. The wind flow induces sound inside the cavity, and then what we're using is microphones to detect it. But it's not an easy problem to solve, largely because one, the structure is rotating, and then it is such a large structure. Wind turbines these days are the largest ones are over 100 meters in length, so they're huge structures. And then another challenge you have is if you're monitoring this entire asset, which represents the wind farm, you can have hundreds or even thousands of turbines. And how do you do that? So it becomes a data acquisition challenge, and lots of sensors to be monitored on a wind farm or on a wind turbine as well. So it becomes a data management problem and also a data collection problem. So there's companies that are doing this now. So for example, this user interface basically highlights, let's say, different turbines. And then with that, you have data centers that are looking at the integrity of and the condition of different turbines in the field. Right now for wind turbines, if you look at this the picture down below, this is from 2011. Not much has changed. There's lots of sensors down at the bottom where you have electrical management systems. And then at the top inside of the nacelle where there's the gearbox, there's the generator, and so on and so forth. There's essentially no sensors on the blades right now. And also the turbines really don't interact between each other. There's not much communication right now. So that's the current state of the art. So the question is, if we can create this digital twin, and if we can have sensors that are distributed, we can do enhanced predictive maintenance, we can improve reliability, improve availability, so basically increase the power production. So there's lots of opportunity in this space for advancement, but there's also lots of challenges as well. So if you want more information about the center and what we do, you can look at uml.edu/Windstar, and my contact information is shown below as well. So with that, I'll stop and answer any questions that you guys have.
Thank you so much, Chris. This is really interesting. Yeah, so being a lay person, I'm coming from a software background, so I'm learning a lot about the I guess the challenges you just presented, and I see a lot of opportunities both on the hardware side, right? You talk about the distributed sensors and then all the way to the pretty large scale data analytics in real time. So this is really fascinating to me. So just a very high level question here. What are some of the greatest challenges that you see, in order to fully realize a real time digitization? As you discussed, right? Creating a high fidelity digital twin of something like that, like a very large, complex structure or a distributed energy system.
So you need distributed sensors. So one of the biggest challenges is power. So powering these sensors and wiring them, because they're not small, right? So a single blade is 100 meters long. And so you have powering issues, you have wiring issues, you have data transmission that needs to be performed. And so, and if you're operating at a high rate, so if you're monitoring in real time, your sampling rate can be 50 kilohertz, something like that, potentially. So that's large amounts of data, especially if you have lots of channels. And so those are some of the significant challenges that we face.
Got it. And certainly there's also a cybersecurity aspect when you have so many sensors on critical infrastructure. But we'll save that for a later part of the conversation, because we have two of our panelists are experts in cybersecurity. I'm sure we'll come back to that. So, and I have a few other questions about the So we'll come back to that. Thank you so much, Chris. Next, we will have Dr. Amir Rahmati. Amir is a assistant professor at the University in the computer science department. He's an expert in cybersecurity, and he leads the Security and Privacy Lab here at Stony Brook. He earned his PhD in computer science and engineering from the University of Michigan in 2017. His research focuses on the security of emerging technologies, including machine learning, deep learning, and Internet of Things, which are all critical enabling technologies for smart infrastructure. His works involve designing, building, and evaluating systems that tackle security challenges in these domains. Dr. Rahmati's research has received frequent attention from media, including MIT Technology Review, Washington Post, and Bloomberg. His work on the security of autonomous driving systems is currently on display at the London Science Museum. So, Amir.
Thank you for the very kind introduction, and thank you everyone for attending this panel. I hope that we have a lively discussion here. So I'm going to briefly talk about some of the research in my lab and some of the challenges that I see in the smart infrastructure domain in terms of security and privacy. All right, as Rong kindly introduced, I lead the IFA Security and Privacy Lab at the Computer Science Department at Stony Brook, and our research focus is primarily on IoT devices and machine learning security and privacy challenges. So today, given the topic of the discussion, I want to talk about some of the characteristics that I see that are unique to smart infrastructures and some of the security and privacy challenges that I see have risen in this space. I think as you hear Jonathan and Christopher talking about the various areas and challenges that they have tackled in their long and distinguished careers, there are a couple of things that, and kind of like points that you may have noticed. First of all, we talked during these talks. We saw many different embedded systems and computing devices used in various tasks, and heterogeneity is one of the challenges that you immediately see when you hear these talks. We're talking about many different manufacturers, each working on their own frameworks, their own platforms, their own devices, and these devices do not necessarily have a common language to talk with one another. Another issue is connectivity. All the sensors that Christopher just talked about, they need to be connected not only to one another, but presumably to some other cloud platform through the internet to be able to transmit data and allow expensive computations to happen and decisions to be made. And so when we're connecting these devices to the internet, we're opening them to a lot of security risks. And also, so we're kind of like risking some of the data that they're collecting to fall in the hand of people who are not supposed to have them. And speaking of data, we heard about the massive amount of data that these sensors and these devices are producing and also consuming. So we're seeing an increased use of machine learning across these platforms as they try to make sense of this large amount of data that's getting collected. So looking at these platforms, many of the old challenges that we had in the security and privacy domain come back and show themselves with new faces. The problem of access control, for example. How do we manage the information that is getting gathered using all these sensors and all these decisions that are being made? How can we provide correct access control that works globally across many of these platforms? We have the issue of software updates. These devices, although they're connected, they're not necessarily well maintained. We have thousands upon thousands of startups working on small projects and trying to bring them to like the wide market as soon as possible. And security is not necessarily the first thing that they have in mind. They have a move quick and break things mentality that doesn't necessarily work well when you take in the security and privacy challenges that arise. And speaking of privacy, all these sensors and data collections that are happening in the wild can have huge privacy implications for the users of these systems. And we have kind of like seen an increased interest in regards to this from both the news media and the government policymakers regarding how our data are control we can maintain on our own data. So as I said, my lab focuses on challenges in two areas. One is Internet of Things and one is machine learning. I'm going to briefly talk about some of the high-level trends that my lab pursue and how we think we can address some of these challenges that I described before. First of all, one of the big challenges in controlling the information and the flow of information in these IoT infrastructures is the problem of information control. And you can think of many different examples of how this can occur in any platform. But as a kind of like a simple toy example, if you think of an application that all the controls one light switch, and for it to work properly, it wants to know your location so that whenever you are or at home or whenever you are in the area that's assigned to that light switch, it will turn on. But of course, this application suddenly has access to your location in real time. And if they wish to abuse it, they can potentially pass it to an outsider who has some level of control over the application. And this is not limited to one application. We're seeing like an increased trend, platforms that try to connect various IoT platforms and smart platforms together. People still might have heard of IFTTT, for example, as a big example, as a known company working in this area, where you create simple if this then that rules that tries to connect these various systems together. And these are not limited to home devices. Even in industrial settings, you have different manufacturers producing different products, and you still need to be able to connect them with one another, and while controlling the information that's going across them. So what we are seeing more and more is that the attackers are noticing these information. They are seeing the security, the risks, and that these platforms can have, and they try to abuse them. Recently, you probably have heard of the Mirai botnet, which infected millions of IoT devices. So what my lab has done, and what we think is kind of like the future in regards to this, is to move from kind of like the traditional access control model, where we think of these permissions as somehow gatekeeping, where your app, your system either has access to the location, to the internet, to a device, or it doesn't. And move toward a world where we can understand and control the flow of information, where we can define that, for example, the location can be used to turn on and off a switch, but the location cannot be shared with the internet. And there are, of course, many different like aspects to this problem. You can think of IoT platforms being able to do this for the apps that are being developed for them. You can think of advertising platforms using this to get only the information they need, rather than kind of like a blind collection of all the user data. And you can think of this as being applied to emerging platforms such as augmented reality systems. On a somewhat similar note, we want to be able to correctly capture user intent in terms of what they want and how they want their data to be used. Different permissions and different pieces of information impose different risks for the user. So it's important to try to understand and distinguish those to be able to provide the users with control that makes sense to them and is beyond the giving them pages and pages of either privacy policies or asking them every minute to approve or disapprove an access control. Another very important thing is cloud integration. We're seeing all these smart platforms being connected to cloud, and computation being shifted to these cloud platforms. So it is important to think how we can kind of like expand on these flow control policy, and to be able to have them across different spaces, and potentially they control how the data is used in a cloud setting. The other part of my lab, another kind of topic we cover, is machine learning security. And this is an increasingly important area of research, mainly because the reach of machine learning right now is kind of like longer than ever. We're seeing machine learning models being able to perform at human level performance on many tasks, being it recognizing objects or solving CAPTCHAs, reading addresses, recognizing faces. And with this human level performance, and they're being adopted more and more across different systems. However, these machine learning models are not perfect, and they're prone to attacks just like any other computing system. And for these models, the attacks can be quite subtle. This is a famous picture that you may have seen from a work back in 2015, where researchers show that by making small, subtle manipulations to the image that is not noticeable to the eye, you can change what state-of-the-art classifier classify an image as. So here on the left, you see an image of a pig, and the classifier classifies the pig with near 100% confidence. But yet, if you add imperceptible noise to it, such as those in the middle, you will end up with an image that to us looks exactly the same, but yet the model will classify as an airliner with a near certainty. And this is not limited to kind of like test time and work of these systems and how they perform in the wild. If the attacker are able to manipulate the training process of these models, they can also cause them to either misbehave in certain ways or have certain blind spots that they aren't able to perform correctly. Here, for example, we have another work from 2017 where it shows that a small perturbation in the training, and by just adding one training example of a dog labeled as a fish, we can change the decision that the model makes on a variety of inputs in the lower section. And another kind of like example that is probably more well-known is the example of Tay. Tay was a bot that was made and put online by Microsoft, I believe, if I'm not mistaken. And it was supposed to be like a communicative bot. And I think Jonathan hit on this point that the technology to have this out in the wild is just not there yet. And what happened is that in less than 24 hours, with all the inputs and interactions that users had with Tay, it suddenly changed into this kind of like racist bot that would respond with very inappropriate comments. So and the thing is, these attacks are not limited to the digital world. Rong mentioned one of our works that's currently on display on the London Science Museum. And in that work, what we showed was that can have real world and physical world manifestations. So you could have a stop sign that is classified as a speed limit by just having some stickers put on it. And you have and these attacks can manifest themselves in different ways. They could be a sticker on a road sign. You could abuse effects such as the rolling shutter effect that I'm showing here to induce these attacks. And you have various systems falling victim to these attacks. You can have air control system and collision systems falling victim to these attacks. And you can have medical devices such as the ICDs fall victim to these attacks. So given all of this, what can we do? So one very well-known technique to defend against these attacks is adversarial training, where just like an attacker during the training time, we calculate possible attacks and we train the model against those attacks during the training time. But one big challenge in this area is that the process of adversarial training is very expensive. And for every model that you have, you need to do this retraining again and again. So any small tweak to the model will require you to go through this robustification technique from the beginning. And one of the important lines of research that my group is following is to see how we can make this robustification process practical, whether it be by decoupling the process of robustifying the model from the training and have basically some sort of filter that allows you, that takes care of the robustification before a data is passed to the model, just like the picture on the left, or whether it is to come up with procedures that allow us to transfer robustness from an already robustified model to a normal model. So that's it for now, and I look forward to discussing these topics, among others, with other panelists.
Well, thank you so much, Amir. This is really interesting. And so earlier in your presentation, you talked about this shifting from an access control view of information security to a more flow-based control model. So really interested in this. So what do you see as the biggest challenge this new paradigm almost?
That's a great question. I think like an important thing that need to be addressed is like coming up with a common language that allows all these platforms to express these permissions and to be able to understand them across their communications. So each kind of like framework on itself may have different levels of access control, and they may have very strong definitions of access control within themselves. But as soon as we go from one platform to another, as soon as we try to connect them, suddenly many of the guarantees that exist falls apart because we just don't have this common language that allows these decisions to kind of get propagated beyond a single platform. So I think like coming up with that language and being able to define that is like the most important step we need to take toward that.
I see. Is this still at the stage? Are you practitioners in the industry already taking it on and exploring it in real world applications?
So we're seeing some use of information flow control mostly during, but it's done mostly in terms of verification or at development time, rather than it being used actively during kind of like the use of these platforms. There are certain research groups in the industry that are kind of playing with these ideas and see how it can potentially be adopted in the real world, but they are still at early stages.
Got it. Thank you, Amir.
Thank you.
Yeah, so before I introduce our next speaker, I just wanted to remind all the participants, please feel free to drop your questions, post it into the Q&A tab. And then after all the intros, we'll come back to the questions. Okay, great. So next we will have Dr. Jennia Hizver. So Dr. Hizver is a principal architect at AT&T. She is recognized as one of AT&T's experts on cybersecurity. She helps customers with designing, building, and implementing networks to ensure that data, applications, and systems remain secure. She has both a deep and wide background in information security, being applied across a wide range of technologies. She is a certified information system security professional and a certified information privacy professional. She holds a PhD in computer science from Stony Brook University. Welcome back, Jenny. And she has published extensively in security research in both papers and presenting her work in premier conferences, with the focus on improving system and network security. Jenny?
Great. Thank you, Ron, for the introduction. It's my pleasure to be here today. Let me share the screen. Okay. Can you hear me?
Yeah.
Okay, great. All right. So again, thank you for the introduction. So I am indeed principal architect at AT&T in the AT&T Cybersecurity organization. I have been with AT&T for over 15 years now. Not only did I do my PhD actually in Stony Brook University, I also did my master's in computer science as well. So I've been with Stony Brook for a long time, and I also reside in Long Island as well. I also teach software security at Berkeley and the master's degree in cybersecurity. I've been with Berkeley for over 4 years. So very excited again to be here as part of the Smart Infrastructure panel. So let me tell you a little bit about what I do at AT&T. As we have heard already from the previous panelists about smart infrastructures, as you can see also from this video, smart infrastructures are very complex ecosystems of machines, components, people that can be taken advantage of by threat actors by launching both conventional and non-conventional attacks. So my job at AT&T involves working with the customers to secure all of these different components, what we call end-to-end. These numerous systems and devices come with their own security. And as we know, the threat protection only as strong as the weakest link. So we can expect that any of the devices in our smart infrastructure could potentially be vulnerable and exposed to attacks. And with all this variety, really there is no single wall that could stop all cyber criminal attacks. However, the attacks on smart systems and infrastructures could have substantial impact, serious impact, because many of the organizations that actually use this kind of systems, they are part of important industries, critical infrastructures. So understanding the attacks and also focusing on increasing awareness about the attacks, training individuals who are involved in operating of these smart systems is critical. So at AT&T, we come across various types of attackers and adversaries, what we call them threat actors. Some of those threat actors are financially motivated. They may be requesting payment in exchange for decrypting information that they may have encrypted as a result of the attacks. Some threat actors could be employed by competitors, for instance, trying to obtain intellectual property, for instance, in the context of smart infrastructure, like an automation logic that the industries employ. And as we can see from some of the screenshots, the industries that I work with actually, it's manufacturing, it's supply chain, medical or healthcare, medical devices, manufacturers, smart cities, smart infrastructure. So all of this could potentially become targets for attackers. So this is what I do at AT&T in essence. I work with customers on protecting the infrastructures, on selecting the best controls that could be adequate for the infrastructures, and that includes a number of domains, such as governance. Governance is where we establish clearly defined roles and responsibilities for individuals within the organizations to protect assets. Software and product security, conducting periodic security analysis of the systems, identifying potential or possible technical weaknesses, conducting data flow checks to ensure that the safety controls work correctly, identity and access management, implementing the mandatory use of access controls, such as use of passwords, implementing centralized identity and access management processes, assigning access privileges to users of the smart infrastructure systems. Data protection identification is also one of the central domains, carrying out assessments of compliance with data regulations to monitor the confidentiality of data. Secure communications. Many of the devices, as Amir mentioned, not necessarily use the common protocols and use the best encryption to protect integrity of the messages. In terms of vulnerability management, establishing a patch management policy, updating, changing configurations, creating backups of the systems. And finally, one of the most critical components that AT&T has significant presence is security operations. So monitoring, collecting events to audit various activities, anomalies on the networks, access to systems with unauthorized privileges. So all of these domains are important and critical to a well-rounded protections of the systems. And that's in essence my job at AT&T. I am basically a hands-on person who makes sure that we have those implementations put in place. So that's pretty much it about my job. So let me return.
Thanks so much, Jenny. So, I guess you were talking about, both you and Amir were talking about cyber attacks, right? So in many different ways. So can you, for a lay person, I think we hear in the news about data breaches and things like that. I remember years ago the massive data breach at Target. I guess it was caused by someone hacking into the refrigeration system, and then somehow got to the credit card database through a back door. So we hear about all these things, but can you, as a practitioner, so can you share some more examples? You talk about, you're focusing very much on, smart manufacturing, supply chain, and in those areas. Can you share some more examples about cyber attacks?
Sure. So smart infrastructure systems specifically are all interdependent and interconnected. And if an attacker is able to compromise one device, like you mentioned in the case of Target, potentially attacker could penetrate the entire network, could access other systems on the network. One example, one of the recent examples would be City of Baltimore. So City of Baltimore had what they call a CAT system. It's a computer-aided dispatch system that supported 911 service calls. So that system was hacked from the internet. Apparently, in the process of some updates on the firewall, the IT department opened certain ports, and through that ports in the firewall, attackers were able to penetrate the network, compromise the CAD system, and that paralyzed the automated handling of those emergency calls. So emergency responders were not able to respond to calls that were coming from the public effectively. So the purpose of that system was essentially distribute the calls in such a way that it was, more efficient for responders to respond and be there on time. So the responders had to take the calls manually. Luckily enough, the issue was identified pretty quickly, and the firewall port was closed. It only lasted for about a few hours. But imagine if this lasted, it was prolonged, the impact could have been significantly more sinister, particularly that we're dealing with such important critical systems like 9/11 emergency system. So that's one example. Another example, very common example that is being used is the Stuxnet example. As you may be aware, in Iran, the nuclear factory was compromised, and malware took control of some of those reactors and paralyzed the production. Think about sometimes, and we have heard from Jonathan and Christopher about sensors and robots. So something as simple and trivial as a sensor, a parking sensor, for instance, or a vending machine, right? You would think that it basically, it's a very simple system, doesn't do much, just but if we compromise a sensor like this or a vending machine, again, we can access other systems connected to the same network and affect the entire critical infrastructure as well. So there is a lot of emphasis on securing the systems in smart infrastructure currently. So.
Amir and John and Chris, feel free to jump in.
I'll give another example. Jonathan spoke about robots. So robots is also a very interesting subject. So robots essentially operate using software, right? That software at the firmware level. So anyone who's able to compromise a robot, able to control the robot. And when it comes to robots, what's important is physical safety, right? Precision and integrity of the operations, right? So physical safety, imagine robots working side by side with humans. And if an attacker is able to control the robot and change the position of the robot or movements of the robot, that could have serious consequences for physical safety of humans. So I think that would be a good example for Jonathan's area of research.
Yeah, well, I've thought of, they have this robot deployed at the supermarket where I go, Stop and Shop. I'm not sure if you've seen this robot. And I can imagine, some malicious person getting in, and because the robot is not perfect, in fact, but you can imagine someone from a competing supermarket or with malicious intent trying to have the robot just run into people to make it really annoying to shop there, and they would lose a lot of customers.
What does the robot do at Stop and Shop?
I think it by and large looks for spills or things that have been fallen off of shelves. And Dave's little hazardous situation. To be honest, it mostly just wanders around, and I think people sort of stare at it, but it's more curiosity. But I think also, you know how Amazon, their factories are outfitted with these robots that move things around very efficiently. You can imagine a malicious competitor, or somebody just malicious in general that doesn't like Amazon, and there are a lot of people like that nowadays, trying to hack into their very sophisticated robotic shipping system. Yeah, I'm waiting for. I'm not that I want such a thing to happen, but it seems inevitable.
It seems inevitable. I actually shop at Stop and Shop. I have met this robot many times. So far, so good. It's been pretty safe. Every time I come across the robot, he kind of steers away from me. Doesn't want to introduce itself. But you are right. Attacks on robotic systems, like for instance, like you brought an example of Amazon, it could result in a stoppage in the production chain or in the distribution chain, right? And that could also have serious consequences in terms of revenue for organizations. So yeah, attacks will, you remember a few years ago, I mean, a decade ago, when people were just starting to use smart devices like a smartphone, and imagining attacks on smartphone was something, not really probable, but as we can see right now, attacks on smart devices are common. So attacks on robots and attacks on sensors are coming out, and there will be more and more of those. So it's time to start thinking seriously about enhancing security of such systems.
Yeah, how have we, as I'm thinking about this, how have we managed to avert this sort of attack on airplane systems? Because it would seem that the same kind of people that would be interested in attacking these robotic systems that are starting to emerge would have also been interested in attacking airlines. How come we haven't seen too much of that? I mean, I don't remember any instance of a airline reservation or even not reservation, the flight control system. Those haven't been attacked, to my knowledge.
And related to that, I was thinking is the drones, right? So Chris, you mentioned, in the utility industry now, there's more, wider use of drones being used for inspection and things like that. So I think that could be a potential concern as well, right? It's if and also I guess the sensors mounted on the critical infrastructures as well.
Yeah, so I mean, drones are being used now to do visual inspection of wind turbines and other structures. The challenge right now is that a photograph, if it's a large area photograph, the resolution is pretty poor. So in order to get informative images, it has to be somewhat smaller to get the resolution that's required. So if that's the case, you're taking hundreds of pictures on a wind turbine, right? And so on a wind farm, you're taking thousands of pictures. And so that's a challenge because there's lots of data. And then the other challenge is that you have to train the data, train whatever machine learning algorithm that you have. And so in order to have those AI or machine learning algorithms work effectively, they have to know what is good and what is bad. And like what Amir showed, right? You can have a dog image that's or something like that. So, and I'm not an AI expert or machine learning expert in image processing in that regard. So being able to interpret damage or areas of concern, that's of growing interest, and no one's really cracked that, solved that problem yet.
Absolutely, and also I think Amir, you worked in self-driving, autonomous vehicles, right? So certainly these are much larger robots compared to the drone. And also, I think Jennia alluded to earlier is you have the human drivers and the autonomous vehicles mingling, I guess, in the road systems. I think that makes it an even bigger challenge.
I think one possible disconnect in the security side is that when robots and robotic, even on many IoT devices, they're going so fast from the research lab to production nowadays that we don't give primary concern to or attention to security. Like when I've never actually, although I'm sort of aware of these security issues that we're talking about, it's not a primary focus of my research. So you can imagine something that seems successful going into production, like I shouldn't mention this, but the basketball system we put into production, there's no security, nothing very secure there. And it could very readily be hacked. And so because I think that's what's happening nowadays. Things go so fast from the research labs into production that there are just all sorts of opportunities for malicious individuals to take advantage.
And that speed of innovation is getting even faster now that we're still in the pandemic, right? So a lot of things change so fast, and new demands and new challenges. And I think I wanted to come back to you, John, about this. Is you were talking about the virtual meeting space, right? The virtual presence technology in the smart conference rooms and things like that. So now that we're gradually back to in-person, and hopefully, certainly, we're still virtual here, right, for this year's conference. Hopefully next year we'll be in person. So where do you see the future of the in-person collaborative environment, or is it going to stay, you know, quite virtual or hybrid? How does the new technology will transform, you know, to make it, you know, more conducive for collaboration?
Yeah, I really can't predict the future so well, but I think that I believe that conferences for forevermore will be hybrid to some extent. I think a challenge for the technology, though, is to keep people very focused. And I think it's just this is a challenge for technology in general. There's so many opportunities. I mean, the minute you allow access to browsing the web, people's just attention go crazy, and devices. How do we have our technology help us focus our attention rather than divert our attention? I think it's a huge challenge for the future. And given that so much of our interaction with each other, even with our loved ones, are intermediated by technology, how do we figure out a way for technology really to tightly connect us rather than be a source of disintermediation?
Right. And then I just wanted to address, we have some participants posting questions, you know, and there's one for you. For your project in Kenya, the RAPID project, what kind of challenges did you have with procuring and deploying repair parts? How did you meet these challenges?
That's a good question. Okay, so some parts were available in Nairobi, so the biggest city by far in Kenya, but often the parts had to come from Holland. Okay, we had partners in Holland, and Holland is a country that focuses a lot on water issues. So we didn't really improve we tried to have as much advance warning when parts were failing and they needed replacement, so that although it took quite a while to get something from, say, The Hague to Nairobi and then to the northern, you know, outer reaches of the country, at least there was this much head start in getting the parts there. Yeah, the key was early warning and getting a head start, getting the stuff there. Yeah, just want to say that.
Got it. And I guess pre-pandemic, so I guess the supply chain challenges weren't as bad as what we're experiencing right now. So I guess that, you know, I guess you know, we're gonna, you know, dive into the supply chain aspects as well. You know, so thinking about that, right? So in order to track things and trade, traceability, want greater transparency, but then on the flip side, security experts, Jenny and Amir, I guess privacy preservation is also, you know, not only privacy, but also, I guess, business secrets and things like that, also critically important. So can you guys chime in on that? So how do we balance these things, right? On one side is protecting from or defending against the cyber attacks and all the snooping and so forth. On the other end, you know, we do want to, you know, the customers and everyone wanted more visibility, more transparency. So can you comment on that, Amir or Jenny?
So I think a very important aspect is that, like, one main challenge that I see in this area is that we're collecting, we seem to be collecting data at some points just for the sake of collecting data. That we are just taking everything in, and then we'll say, okay, we'll figure out how we can use it later. And this kind of like mass collection causes this issue where, while you may need certain data points on certain aspects of a matter, because you're collecting so much data, it is hard for you to understand your data, and it's hard for you to make judgment about the privacy risks associated with those data. So one like approach that I really advise is that for us to try to understand what do we really need to get in each case. And a good example of this that I've discussed with some of these companies before is the matter of advertising. So for the advertisement, you have these advertisement platforms that are kind of like the core and the back end of the internet. They support like the economy of the internet. But because we're just shifted to this massive data collection, they're just getting everything about us rather than maybe the things that they need to correctly target advertisement for us. Let's say if you want to know about if they want to recommend a restaurant to you, they don't care about necessarily about like what kind of shirts you prefer or where do you go at certain times. They would like to know what restaurants you visit. They would like to know what foods you like. But that is the extent of the knowledge they need. And everything beyond that would be unnecessary data for them to collect and analyze. And in pretty much in any application, you can think of this kind of like unnecessary data collection that is happening, that is then will lead to catastrophes when some data leak happens. And you see like massive amount of user data being exposed when even the collection of it and the storage of it wasn't necessary.
Absolutely, and we see that and hear about that quite often, right? So like, sensitive data, being hacked from the database at the school district, or something like that, right? So and it happens quite often. I wanted to, we have a few more minutes left, so I wanted to shift gears to back to the energy industry, the utilities. Chris, so there's actually a question in the Q&A section about you. In your presentation, you talked about the sensors mounted on the wind turbines. The wiring you mentioned, that's one of the challenges. So the question is, has the industry been jumping on the wireless sensors and cellular connectivity using LTE, Cat-M or other standards, 5G standards? Can you please comment on that?
Yeah, so I'm not aware of a lot of industry sensors that are using wireless right now. There's a cost associated with that, right? So in order to have a link of data, you have to pay for it through a network. Most of the sensors on a wind turbine are hardwired, and data is transmitted that way. There's not a lot of sensors that I'm aware of. For other industries, I think that's probably true as well. So like if you're monitoring bridges and other forms of like solar farms and things like that, I think most of the things are wired. So I think there's lots of room for opportunity.
Yeah, I have a question for you on another angle. Okay, so I recently was in California and I noticed massive wind farms, especially in the Mojave Desert. But so many of these turbines are just not operational. And I was wondering, is that efficient? I know that, for example, my experience in data centers, at this point, most data centers, they don't fix machines. They just shift, as the machine is failing, they shift the workload and they just totally replace they get rid of the old machine and replace it with a new one. My environmentalist says, oh, this is a horrible thing. We're just throwing away things instead of fixing them. And I felt like, oh, is this actually happening in the wind turbine industry too? These massive structures, as soon as they fail, we just toss them. That would be such an environmental catastrophe. Anyway, what can you
So there's a few reasons why wind turbines don't operate. I can't speak for the ones that you particularly saw, so I'm not familiar with that wind farm. But I know that, in California, there is an area that is full of wind turbines that are really small. And these small turbines, they generate so little power in comparison. You can replace like 100 small turbines with one single wind turbine, right? So it all boils down to cost of energy, and so operating costs are part of that. So I don't want to speak specifically on that case because I wind farm, but it's not inconceivable. But there's other reasons why wind turbines don't turn, and so if there is wind and it's not, there is also they could be down for repair or maintenance or something like that. And another thing that can happen is what's called curtailment. If there is an excess supply of energy on the grid and renewable energy, and that's becoming more and more prevalent, unfortunately, and it will continue to do so because there's lots more of renewables coming onto the grid. But so there's an oversupply of energy, and so instead of having and the cost of electricity actually goes negative, and so owner operators actually have to pay to have the electricity go onto the grid. So instead, what they do is they shut down or curtail the turbines, and that's true with solar assets as well. And that's part of the problem with renewables is that if we're to go to carbon neutral and we want to have all renewable energy, well, we need to have more than just what we need. We need, because there's such variability. So curtailments will take place. And I don't know specifically, John, whether you were in a situation where you saw curtailments actually happening, or there was some sort of repair or maintenance going on, or the turbines were obsolete and they just said, well, let's just turn them off and not run them. So it's one of those three possible things.
Okay, thanks. Yeah.
So, thinking about the again, if we stay in the utility industry, and also I think there's initiatives in New York to I guess the offshore wind farm initiatives. I guess we're going to see massive wind farms off the shore of Long Island in the next few years.
It's likely.
Yeah. So I know some of our colleagues in the over at the Energy Center next door. They are part of the some of those projects. So I wanted to ask. Amir, you talked about a cloud integration in your presentation, right? So that's so. For me, most of my projects here at CEWIT were running it on the cloud, whether it is, and over the years, there were, pushbacks, especially we do a lot of work in healthcare and medicine. So in the early years, there were a lot of pushbacks, in terms of, HIPAA and things like that, right? So concerns about, preserving patient privacy and sensitive data. That has changed quite a bit over the past few years. I wanted to ask industry experts on the panel, where do you see the cloud integration in, say, utilities industry and energy and in other parts, in manufacturing and retail and supply chain. So I just wanted to, try to get your perspectives if we can. John, Chris, Jenny, feel free to jump in.
I don't have much to add to that question, so I'll let the others go.
Yeah, because I was thinking especially, and add to that is the wrinkle of more video data, right? So Amir, you talked about the large amount of data being collected, right? So, and it's not just sensor data anymore, right? There's a lot of unstructured data being captured by cameras, by drones, by VR and AR devices, so to speak. So I think there's going to be and related to that. I know we're getting into overtime here. Is so smart infrastructure is such a interdisciplinary field, right? So we have experts, we have mathematicians, we have cybersecurity experts, we have, mechanical engineering and renewable energy experts on this panel. So it's quite an interdisciplinary field. It takes on a lot of different background and experience and knowledge. Is there a push for some standardization effort across the different sectors? And of course, I think cybersecurity is front and center. AI, the earlier panel on applied AI discussed in great length about explainable AI, right? When AI models, they can't be black boxes. It needs to be a human in the loop. So all of these things, I think it takes in a lot of things from different angles. So is there an effort, coordinated effort to enhance standardization, interoperability from a security standpoint, but making the system smarter and make it more user friendly?
Well, one thing I know of is that at least in sensor data, there's some sort of, there are event models. There's certain models that people deploy the data coming from sensors. So I think those are, I'm not an expert, but that's becoming somewhat standardized. Yeah, beyond that, I don't know.
I think that in terms of industries are trying to standardize, but it's really application specific. So if you bridge, it's going to be different than it is for a wind turbine, because the conditions are different. Same thing with an airplane or something like that. It's so different. So and it really depends upon the environment that the sensors are operating in. On the software side of things, I'm not sure about the standardization.
Right. I think on the software side, it's more, I guess, again, I'm just, not having the domain knowledge is certainly the push for more open source and more open standard has been, going on for many years. But some of these, critical infrastructures are in very regulated and protected environments, just like, I guess, healthcare infrastructure. So I think we see a slow opening of embracing these open standards, so to speak. But I'm just curious. I think
I think, as Christopher mentioned, these are happening, but they're usually very domain specific. For example, I personally know of the I think it's called the Connectivity Standard Alliance, where the big players in the smart home industry are trying to come up with a common standard for communication in a smart home environment. So you have these kind of special, niche areas that are slowly ramping up to building these standards, but they're still very much disconnected from one another. So if you have a standard for smart homes, it has not necessarily have anything to do with a standard that you have developed for communication across the energy network, or for traffic management, or any other aspect that you would expect have to work together in a smart industry. So,
and sometimes they're competing also.
Exactly.
Yeah. So I mean, I think as you said, Amir, in the build home segment, there's like the building information model, BIM, and then there's also the Google Home. They don't completely cover the same ground, but they're not in a total agreement. And I think but anyway, I think that probably that area is more advanced in terms of standardization and the push to standardization than others. Just because there's so many homeowners that are interested, it would benefit everybody if there was standardization. In some other cases, yeah, I mean, it's a global good, but not necessarily good for the manufacturers.
So I'll add in a couple of just comments that I didn't mention. As we said, it depends upon the sensors that you use, depend upon the environment. And if you're in a home environment, well, that's a pretty benign place to be. It's not going to rain if you're inside, right? If Google sensors or whatever. temperature doesn't vary that much, but if you're outside in a wind turbine, it's a harsh environment. There's vibration, there's temperature swings, there's humidity, there's lightning, things like that. So one thing with regards to sensors, environment is the critical thing. Sensors have to be designed for the environment they're working in. And also the other thing is a lifespan is an issue, right? So if you have a sensor that's mounted onto something that's like a bridge or a wind turbine, and the sensor's mean time between failure is 10 years, but your asset is 20 years or 50 years, well, it's not really, is it the sensor that failed or is it the structure that failed? And so it really is environmental. It's really application specific, I'd say.
Right. And then going back to that question from the audience is if we do incorporate wireless communication into this equation, I guess that's another part of the durability, right? And also the robustness
Yes.
in harsh weather and harsh conditions, right?
So,
right. So
I know when I'm using Bluetooth in my house, I turn my microwave oven on and the Bluetooth stops working. With interference and things like that, if we're relying on, if there's what's called critical safety items, maybe not for wind turbines, but for, let's say, a helicopter or something like that, right? And if you're relying on data communication or network connectivity and that disappears and you're not getting the information you need, there's a reliability issue there. So,
but that could be opportunity for more innovation and
yeah, that's right. We need better wireless. I mean, we've come a long way, and there's no doubt, but we've got a way to go for sure in terms of reliability and trust.
Certainly, I think my colleagues here at CEWIT and also some of the partner companies are in that field. So certainly, I think we'd love to carry on with that conversation. So with that, I think it's time to wrap up this really informative and exciting panel. I'd like to express my gratitude to all of our esteemed panelists. Thank you so much for making time out of your very busy schedule to share with us your experience, your insights, and your vision on this super important topic. Greatly appreciate it. And also on behalf of the CEWIT Program Committee, I'd like to thank everyone who joined us today. After the conference, as you probably already know, the video will be shared, and my colleague Gina will send out a survey to get your feedback and suggestions. And feel free to send us if you have any additional questions or comments. For the panelists, please feel free to reach out to us, and we'll pass them along to our panelists. And certainly follow them on LinkedIn. So these are our preeminent experts in this field. So thank you so much to everybody, and in our next year's conference. Thank you so much.